In this video, we want to talk about analytic functions. What are analytic functions? Analytic functions are, functions that are complex equivalents of differentiable functions in real analysis. Analytic functions are very, very important in complex analysis because, one, they have elegant properties and they are much stronger than differentiable functions. Now, how do we define them mathematically? As you can see, we said let f of z be a complex function where z is equal to x plus iy. Z is a complex number. The function f of z, this function, is analytic at a point z0 if it is differentiable at every point in some neighborhood of z0. So that is how, just like saying you have a point, now, and you have this z0 to be center of this ball. Now, this particular, the function f of z, which defines the ball, is analytic if at every neighborhood of this z0, that function is differentiable. And f is said to be analytic at every point of a domain of the complex number, the domain of, let's say, domain D, which is a subset of the complex number. So f is analytic at every point. If f is analytic at every point, then it's said to be analytic at all points on the domain of that set of complex number. That is about that definition. Now let's look at the conditions that analytic functions must satisfy before they could be said to be referred to as analytic function, before they could be referred to as analytic. What are those conditions? But before we go into that, like we have said here, we mentioned the word differentiable. So that means before a function could be analytic, it must be differentiable. Okay? It must be differentiable. So now let's look at differentiability and analyticity. Now, for a function to be analytic, it must be differentiable at a point. And if it is differentiable at every point in that domain, it is said to be analytic. Okay? Now, but there is a particular condition that a differentiable function in complex analysis must satisfy. The condition is that a differentiable function in complex analysis must satisfy what we call a Cauchy-Riemann equation. And not only satisfying it, the function that will be analytic on that domain, must have, the functions, the equivalent of that, the real value functions in that particular domain, they must have continuous partial derivatives. This is what I'm saying. I will give you an example. I will give you a very good example. Now, let f of z be equals to u of x, y plus v of, plus iv of x, y. Okay? Where u and v are real value functions. They are real value functions. They are real value functions of two variables. They are real value function of two variables x and y. You can see. Okay. Now, for this function f, for f to be differentiable, at a point, in that domain, it must satisfy the Cauchy-Riemann equations. And not only that, because this is just the necessary condition for that function to be differentiable. Now the sufficient condition for this function to be differentiable is that the real value functions u and v, they must have continuous partial derivatives. Okay. Now, what do we mean by having continuous partial derivatives? That means that at all points within that domain, they must be continuous partially. Illustrate this concept with relevant examples. Let's look at polynomial function. This example 1. Let f of z be equal to z squared. We want to find out whether this function f of z is equal to z squared is analytic. Now, this will be f of z is equal to x plus iy squared. So by the time we expand this, we're going to have x squared plus 2ixy, then minus y squared. Because remember, I squared is equals to minus 1. So minus 1 multiplying y squared, you have minus y squared. By the time you expand this. Okay, so you can write as x squared, you try to collect like terms, minus y squared plus 2ixy. Okay, beautiful. So now we separate into the real parts and the imaginary part. So the real part from f of z is equal to u of x comma y plus v iv of x comma y. Here we have u of x comma y will be x squared minus y squared. Okay, so and v, taking the component of the imaginary one, the one that has I, I is there. So v of x comma y will be 2xy. So when you consider the one with the imaginary parts. Okay, so now checking whether it is analytic using Cauchy-Riemann equation. Partial derivative of u with respect to x is equal to 2x. Okay, and partial derivative of u with respect to y here will be equal to minus 2y. I hope you are getting that. So partial derivative of v with respect to x will be equal to what? 2y. I hope you understand that. I got that. V, then you are differentiating partially with respect to x, so it will remain y. And partial derivative of v as well with respect to y will be equal to 2x. So, okay, now, and what does Cauchy-Riemann says? It says that partial derivative of u with respect to x must be equal to what? Partial derivative of v with respect to y. And partial derivative of u with respect to y must be equal to minus partial derivative of v with respect to x. So with that, let's check here. Let's check. So let's write it. Let's write this. Let's check by writing this. Want to check? Wow, I've cleaned it up. So we want to check the partial derivative of u with respect to x. Is it the same thing as partial derivative of u with respect to y? And partial derivative of u with respect to y, is it the same thing as minus partial derivative of v with respect to x? So the u dx in our case was what? 2x. We got 2x. So which is the same thing as dv dy, 2x. That's beautiful. That's correct. Now the u dy in the case we got minus 2y is equals to, and minus dv dx, our dv dx was what? 2y. So now here minus our du dy was minus 2y. Okay, so if you multiply through by minus sign, this one got 2y is equals to minus 2y. So we are saying that the u dx, the u dy should be equal to minus of what you have as dv dx. I hope you understand that. We have done that before. Let me remind us. We said u of x comma y should be equal to x squared minus y squared. So when you differentiate u with respect to y, the u with respect to y, we have minus 2y. You can see. And when differentiated the v, with respect to x, we got 2y. So if you put minus there, it becomes minus. You can see that, sorry, both of them will be minus. So that means the u dy is equals to minus the v dx. So that's about that. Let's solve one more example. To understand the concept better. Let's solve one more example. Now, this is an example. It's an exponential problem. It's an exponential function. Let f of z is equals to exponential z. Okay? This could be written as what? Exponential x plus iy. Because our z is same thing as x plus iy. Okay. So by the time we expand this, we have what? Exponential x dot exponential iy. So which could be written as what? Exponential x multiplied by cos, because it has cos y plus sine y. Okay? Cos y plus I sine y. I sine y. Sorry about that. Because we have a high there. So now what we're going to do now is we expand this. We have what? Exponential x cos y plus I sine y, or you can write I sine y exponential x, or you can write exponential x I sine y. Are we together now? So in this case now, we have two different variables. We have the one that is real, and we have the one that is complex, or that is imaginary rather. So taking u, let u of x comma y be equal to what? Exponential s cos y. So the u dx there, partial derivative of u with respect to x, will be equal to, that is we are differentiating x. When you differentiate exponential x, it will still be what? Exponential x. So whatever you get now, you multiply it by this. You have exponential s cos y. Because this is a constant, you multiply it by a constant y. Okay, the constant here is cos y. Now, for the u, partial derivative of u with respect to y, that will be, if you differentiate y here, this is going to be minus sine y, multiplied by this constant, that is minus exponential x sine y. I hope you understand. If you differentiate cos y, you're going to have minus sine y. So you use this exponential x to multiply it, because it's a constant. Why? Because you are differentiating with respect to y. So any value of x here will be a constant. So that's how that is. And now for v of s comma y is equal to, you remove I here because it's already taking care of the virtual. So you don't need to include I when you are writing it here. You are considering the virtual size, the virtual, aspect of the expression or equation. So that will be what's up? Exponential x sine y. Okay? Or write sine y exponential x, exponential x is the same thing. So now the v dx here, is the same thing as what? Exponential x, because you are differentiating exponential x, and exponential x is still exponential x multiplied by the constant this exponential x sine y. Then the v dy, that is partial derivative of v with respect to y, it is why you are differentiating now. So that means sine y will give you cos y multiplied by this exponential x cos y. Let's now check using our Cauchy-Riemann equation. Let me clean just this so that I won't have to repeat that again. Let's want to check whether partial derivative of u with respect to x is equal to partial derivative of v with respect to y, or partial derivative of u with respect to v is equal to minus partial derivative of v with respect to x. Let's check. Okay, the u dx here, the u dx was exponential x cos y is equal to, let's check, is it equal to dv dy? Our dv dy is wow, that's it, exponential x cos y. That is satisfied. Now the third one here, and the second one, du dv. Our du dv is what? du dv is what? This is dv dx, du dx. Sorry, it can't be du dv, it's du dy. Sorry about that. It can't be du dv. So our du dy is this whole. Yes, du dy is minus exponential x sine y is equal to, now the v dx. The v dx is what? Exponential x sine y is going to be minus, so you can see that it's the same thing. It's already, the minus must be there as part of the formula, and the v dx itself is exponential x sine y. So you can see that what you have on the right is what you have on the left here. So that means for these two to be equal to each other, it means that function is analytic and differentiable. Okay, it's very, very analytic and differentiable because it satisfies differentiability, and at the same time it's analytic because it satisfies Cauchy-Riemann equations. Now let's look at this third example. Let's Let's look at the third example. Let's look at the third example. This example says that we want to check whether this is analytic or not. This is a complex conjugate of our complex number z. Let's check. You know, in complex conjugate, it means that if z is equals to x plus iy, the complex conjugate will be what? X minus iy. Just change the sign here. So that means what? This will be what? X minus iy. Now, how do we go about this? As simple as we used to do. So let's say let's u of s comma y, you know, be equal to, this one has real variable. There's no I there. And this one has, you know, virtual variable. That's I there. So the u dx will be, this one will be 1, and the u dy will be 0, because it doesn't have this value does not have a 0. I mean, it does not have a y. It doesn't have y variable, so it will be 0. The u dy is 0. This is x. You are differentiating with respect to y, so y will be 0 there. The u dy will be 0. Now the v dx, what's our v? Okay, let's write out our v as well. Our v of s comma y will be what? You know, we are considering the virtual part of the complex number. That will be minus y. Minus y. You don't need to include I here again, okay? Because I is already for v. So now the v dx here will what? Will be 0 automatically, because this value does not contain an x variable, and the v dy, you know, will be what? Minus 1. So let's now check. We check for the u dx is equals to the v dy. Obviously, without wasting our time, the u dx is 1, the v dx is minus 1. So 1 is not equals to minus 1. So this particular function is not analytic. So I remain Dr. Oji. Do well to, you know, subscribe to my video channel, click the notification bell, so that each time I upload new video, you'll be duly notified. There is still going to be more of this in subsequent videos. Stay blessed.